In this video, we will look at how to go from velocity to acceleration and back from acceleration to velocity. Velocity is the rate of change of position with time, that is dx over dt in one dimension. Similarly, acceleration is the rate of change of velocity with time, and so it can be written as dv over dt, or the second derivative of x with respect to time. Graphically, we know that a derivative corresponds to a slope, and so the slope of a v versus t graph gives us the acceleration at that time. Here we have a v versus t graph where the velocity is initially a constant -2 meters per second, but then around 3 seconds jumps up to -1 meters per second. We see that the corresponding acceleration versus time graph is initially flat, and then spikes, and then is flat again. This makes sense because initially the velocity was constant, and then when the velocity increased or became less negative, the acceleration was positive, and then when the velocity was constant again, the acceleration was zero. Just as we can go from velocity back to position by integration, we can go from acceleration back to velocity through integration. We start with a is equal to dv over dt, rearrange it to a dt is equal to dv, and then we integrate both sides. On this side, the integration is with respect to v. We can see this because of the dv. And so our limits are velocities, v0 to v1. Here the integration is with respect to t, and so the limits are times, t0 to t1. This side can be easily integrated to just v1 minus v0, and this side depends on exactly what function of time the acceleration is. However, even without knowing exactly the form of acceleration, we can see that integral a dt is equal to v1 minus v0. This is the change in velocity, and this side can be interpreted as the area under the curve in an acceleration versus time graph. Once again, the area under the curve in an acceleration versus time graph gives us the change in velocity. One small reminder, it gives the change in velocity, not just the velocity. So if you want to find the final velocity, you do need to know what the starting velocity was. And then the final velocity will be starting velocity plus change in velocity. For example, if we are given an a versus t graph that looks like this, which is mostly 0, but between 1 and 2 seconds there's a positive acceleration, and between 5 and 6 seconds there's a negative acceleration, then the corresponding v versus t graph will look like this. We have assumed that the initial velocity is 0. Then between 1 and 2 seconds we see that there's a positive constant acceleration, which means that there will be a positive constant slope in the v versus t graph. Between 2 and 5 the acceleration is 0 again, which means the velocity stays constant. And then between 5 and 6 the acceleration is negative, which means there will be a negative constant slope on the velocity versus time graph. We can also see that the positive area here is cancelled out by the negative area here, and so the total change in velocity is 0. And when the acceleration is 0 here, the velocity stays constant at 0. Here's another example. We are given an acceleration versus time graph. We can assume that the initial velocity is 0, and we are asked to sketch the v versus t graph. As before, it's usually a good idea when given such a graph to draw drop lines at the transition points. We can see there's a transition here and a transition here. These are the drop lines. Pause the video a moment. Try and draw the v versus t graph yourself, and then compare to the answer. We will now proceed with the answer. We see that in the first part, the acceleration is positive, but is decreasing from some positive number to 0. And so the slope in the v versus t graph will start out positive, but will decrease to 0. And that is what we see over here. In the second part, the acceleration increases from 0 to some positive value. And so we see that the slope here goes from 0 to some positive value. And in this last section, we see that the acceleration is constant and positive, which means that the velocity versus time graph will have a constant positive slope. Looking overall at this part, we see that the acceleration increases to a particular value and then stays constant. And similarly, the slope increases to a particular value and then stays constant. Since the acceleration is changing linearly over here, the velocity is changing quadratically. Since the acceleration is constant over here, the velocity is linear over here. Of course, you are not always given a graph. Sometimes you will be given an equation. In this question, the acceleration of the particle is given by a as a function of time is 2t plus 8. If the initial velocity is 12 meters per second, at what times is the velocity 0? There is no answer slide following this, but pause the video and take a moment and try and solve this by yourself. I will tell you what the answer is, but without showing the steps. If you have questions, feel free to come and ask. The answer is D, -6 and -2 seconds. That's the end of this video. I'll see you in the next.